Welcome to aminacademy.com. In physics, let us discuss about thermal expansion. You may notice that sometimes sealed bottles with metallic lids are so tightly screwed that one has to put the lid on a hot water for some time to open it. This would allow the metallic lid to expand. Because of the heating, that metal is tendency to expand. That means this tendency allow the metallic lid to expand, thereby loosening it unscrew easily. In case of liquids, you may have observed that mercury in a thermometer rises when the thermometer is put in slightly warm water. If we take out the thermometer from the warm water, the level of mercury falls again. Similarly, in case of gases, a balloon partially inflated in a cool room may expand to full size when placed in warm water. On the other hand, fully inflated balloon when immersed in cold water would start shrinking due to contraction of the air inside. It is our common experience that most substances expand on heating and contract on the cooling. You may notice further about the railway road that in between the roads they give a little gap between two metallic lines. Since when heat heat is more, what happened that road expand. If there is no gap in between, there is no gap. What happened? Due to expansion, it hit both gaps, both end heads, and may the railroad may bend. To stop this bending, we have to give a little gap between two metallic ends of the road. Now we'll discuss about thermal expansion is the tendency of a matter to change in volume in response to temperature alteration. When a substance is heated, its particles move more and more, thus maintain a greater average separation. Since thermosets are used in solid form, they undergo linear thermal expansion. Now we'll discuss about types of thermal expansion. There are three types of thermal expansions: linear expansions, volume expansion, and area expansion. First we'll discuss about linear expansion. When heat is passed to a solid material and the material expands along its length, it is known as linear expansion. For example, consider a rod of length L and suppose that the temperature of the rod is increased by a small amount, then the linear expansion is given by delta L by L equal L alpha L into L delta T. Here delta L is change in length, L is original length. Here alpha is the linear coefficient of thermal expansion and L is the original length of the rod. Delta T is change in temperature. In SI units per degree Celsius and the CGS units, it is per Kelvin, that is K power minus 1. Look at this figure. This is L0, the original length at temperature T0, initial temperature. After giving heat, what happened? Its length increased with delta L. That means L plus delta L is after increasing the length of the rod is L plus delta L. The temperature increases T0 plus delta T. And if you are keeping the temperature same, the length will be increased length stop. And if you cool down, that length comes to original position. Volume expansion. When a solid increases in volume on being heated, it is called volume expansion. For an initial volume V and delta T, that is change in temperature, volume expansion is given by dV equal to V gamma delta T, where gamma is the coefficient of volume expansion, delta T is the change in temperature, delta V is the volume change. Here, therefore, volume change is V original volume into coefficient of volume expansion and change in temperature. Look at this. This is initial volume. After giving heat, it gives expansion throughout the volume. So its a final volume is big. Volume expansion in temperature increases, gives this picture. Now, area or superficial expansion. If the surface area of a solid increases on being heated, it is called area or superficial expansion. If the area of the solid, if area of the solid is at A0 at 0 degrees Celsius, here this original, then the area of that solid at T degrees Celsius is given by delta A equal to A0 original volume beta into delta T, where B is the coefficient of, B is called, B is called coefficient of superficial expansion, and the unit is given by per centigrade or per Kelvin. Look at this original area at temperature T0, and after temperature increase, that is T0 plus delta T. Area expansion on temperature change. These are three coefficients of expansion we discussed. Now we'll derive derivation of the relation between three coefficients of thermal expansions: linear, volume, and superficial. Derive the relation between the coefficient of linear expansion and coefficient of superficial expansion. Look at this explanation. For coefficient of linear expansion, we know that L equal L0 into 1 plus alpha delta T, where L and L0 are the length of the material after and before the expansion. Delta T is the change in temperature and alpha is the coefficient of linear expansion. For coefficient of superficial expansion, that is areal expansion, A equal A0 into 1 plus beta delta T. The coefficient of linear expansion, where A and A0 are the areas of the material, delta T is the change in temperature, and beta is the coefficient of superficial expansion. Look at these two expansions, that is linear and areal. There is a relation comparing both coefficient to L equal to beta. That means 2 times linear expansion is equal to areal expansion. That is superficial expansion. Derive the relation between the coefficient of linear expansion and coefficient of cubical expansion. For coefficient of linear expansion, we know that L equal to L0 into 1 plus alpha delta T, where L and L0 are the length of the material. Delta T is the change in temperature and alpha is the coefficient of linear expansion. For coefficient of cubical expansion, V equal to V0 into 1 plus gamma delta T, where V and V0 are the volumes of the material. Delta T is the change in temperature and gamma is the coefficient of cubical expansion. From this comparing linear expansion and volume expansion, there is a relation between 3 into linear expansion equal to volumetrical expansion. That is 3 alpha equal to gamma. Comparing all these three expansions, we can derive, that is alpha ratio beta ratio gamma equal alpha into 2 alpha into alpha ratio 2 alpha ratio 3 alpha. Therefore, from this we can say alpha beta gamma, alpha ratio beta gamma ratio gamma equal 1 is to 2 is to 3. Therefore, alpha equal to 2 beta, alpha equal to 3 beta into Therefore, alpha equal to, no, not this relation, we have to, so we have the relation alpha equal to 2 beta equal to 3 gamma. So far we have done about the definition of expansion, thermal expansions, and the types of that expansion and its derivation. We have done. Please subscribe our YouTube channel.